Hello everyone, my name is Jozef Lelic. I work in Salsita as a full-stack developer, and over the past year or so, I've tackled a couple of augmented reality projects. Today I'm going to talk about what augmented reality means and in what shapes and sizes does it come on mobile devices, with focus on the mobile browsers. In short, augmented reality is an enhanced version of the real world that you can achieve by overlaying some sort of virtual digital content over it. If you look at the picture on the right, the boring real world street can suddenly become this magical world if you place a Pokemon on it in a way that it makes it seem it actually stands there. As augmented reality, we generally consider experiences that are, at least to some degree, interactive. That means you just take a picture and then draw something on it in Photoshop. We wouldn't really consider it augmented reality by this definition. I'm sure all of you have heard of virtual reality, and it might get a little bit confusing about how it's different from the augmented one. While in AR, you mix the real world with the virtual one. In VR, the world you are experiencing is purely virtual. You can see on the right that in this VR Pokemon game, the entire street is completely virtual, so there are no elements of real life. But that also means that you need to have some kind of VR headset that you put on your head, so you can get fully immersed in this VR world. While for the AR, just having AR-compatible device is enough. That pretty much means any phone that's still in use, basically. Another difference is that virtual reality doesn't really care about what's around it in the real world because it simulates the entire world by itself. Well, again, the augmented reality needs to have some sort of sense about how the world is positioned, what the environment looks like, where the ground or walls, stuff like that. That would make it seem that augmented reality is more performance heavy. However, the opposite is actually the case because for virtual reality, you need much more FPS to deliver a satisfying experience. I think the usual target is around 90 FPS, and if you go lower in virtual reality, then the users can experience some nausea or other negative effects like disorientation, because the world will be moving slower than they are used to. In augmented reality, it's usually enough if you hit like 30 FPS. So that's when you can save on performance. And also, of course, in virtual reality, you have two displays, which again requires more performance. With that out of the way, let's focus on AR now and the uses it has in the modern world. So I mentioned the game, but there are some others, more serious ones. The ones that are probably most obvious for us in Salsita is e-commerce. You can recognize the screenshot from the Kilo app. Kilo is a company that sells furniture that's highly customizable. So by adding AR experience to the application, we can allow the customers to see how the furniture would look in their apartment before they even buy it. And they can move it around, rotate it however they want, change the color, size, whatever, you get the idea. Another nice use of AR is education. In this example, let's say you are studying anatomy. You can grab a phone and there are already apps that can display this kind of skeleton in front of you, and you can look at it from all the angles with your phone. You can interact with different points on it. You can hide or show like different layers. So it's much, much more useful than just looking at it in a regular paper book. With the AR, you can also translate the text directly that you see with your camera. There are several advantages to it. For example, the text can be too long and you don't want to manually retype 3 paragraphs into your phone. But also other than laziness, it also solves another huge problem, and that's special characters, as you can see on the picture. For most people, it may be pretty difficult to write something in Cyrillic or some Asian alphabets. So with AR, you can just point your phone to the text and get a translation almost immediately. And that's pretty cool. Last use case I'm going to mention is navigation. I think that's just obvious. You can have your navigation that will highlight the road you want the user to drive on. You can show different points of interest that the user would otherwise miss. So all these different use cases can require a different type of AR. There isn't any rigid classification of the types, but based on how the AR experience encores its virtual content to the world, we can split it into a few categories. This list is by no means exhaustive. You can see that all of them have some form of tracking in their name. So let's have a look at the simplest one, the marker-based. For marker-based augmented reality, you basically have a marker with some specific feature, like it should have a black border, maybe some QR code, or something else that's easily recognizable. And then your app can use a library with, that uses some computer vision to detect where the marker is positioned on the picture and under what angle. And it can display a 3D model that in a way that would fit directly on that marker. This doesn't seem as cool as some of the examples that I mentioned before. However, it still has some uses. For example, we're talking about studying anatomy. So on the page with skeleton, you can have a marker, and if you scan it with your phone, it can make a skeleton appear on the marker. Or I believe Lego had a marketing campaign where they put these kinds of markers on their boxes with Lego, and you can scan the box, and Lego figure that's inside the box will appear in front of you. Some other types that were mentioned on the previous slide works in a similar way, just the anchor is of different type. So for example, image tracking, same stuff as marker tracking, except you have any kind of image. Face detection, again, detects your face and puts something on it or above it, next to it. You get the idea. And object detection works also in a similar way, but with 3D objects. Let's say you don't want to have any kind of markers in the world, you just want your user to point the camera in the world and automatically something. Then maybe you would be interested in location-based augmented reality. Instead of anchors, it uses GPS coordinates to place the virtual content in the world. Unfortunately, the accuracy is really low because the technology just isn't there yet. It still has some uses, especially when it gets combined with other types of tracking. So in our navigation example, they actually used GPS coordinates to find out where the car is in the world, and then they further process the camera image to find where exactly is the road that the user is supposed to drive on and highlight that. I promised you we would look into how AR works in mobile browsers. There are many frameworks and libraries that can help us with implementing AR into our web apps. It's a constantly evolving technology though, so there are many new libraries that come and go almost every month. Obviously, can't mention all of them, but these 6 or 7 are good to know about because they all feel some kind of niche. I'm going to run quickly through some of them, and then we'll have a deeper look into Pxr, as I feel that's the one with the most potential in the future. ARJS. It supports marker tracking, image tracking, location-based tracking. Like I said, those are not really the most exciting types of tracking, but still, if for some reason you're fine with just marker tracking, then this may be the way to go. Its main advantage is that it's widely supported on many devices. So if that's something that you want, the support across many phones and platforms, you won't probably want to choose ARJS. Chili's AR has a special feature compared to others. Free AR libraries in that it supports face detection or object detection. So again, if you want something simple, but you want to detect faces, either for e-commerce purposes like putting a hat or glasses on a person, or just do some face swaps, face filters, then you can choose Chili's AR. What if you want something much more robust and not simple as the other two libraries that I mentioned? Then there's It supports full world tracking, face effects, image tracking. It has a plethora of features that I can't really go into right now. But its main disadvantage is that it's paid, so it's not open source. You can't really dig deep into the code, and yeah, you also have to pay for it. But still, if you want to make some huge AR project and you want all the cool features, especially the world tracking, that works on both iOS and Android, you should definitely consider Idle. Okay, Pxr Api. This one is not really a library, rather than an experimental set of API that aims to bring together VR and AR under one roof. By the way, X in the name stands for mixed, so it means mixed reality. WebXR replaces WebVR, but also WebAR, although that was never really a standard. VR part of the WebXR is fully functional at the moment, since it was just as a replacement from WebVR. But the AR part is still being worked on. That means it's not supported on iOS, although according to the WebKit feature status page, it's in development. It has been so for the last couple of months. Main advantage of Pxr or other free libraries is that it supports full world tracking. And that thanks to its interaction with ARCore and probably ARKit when iOS version gets released. I mentioned ARCore and ARKit. What are they? They are frameworks for native AR mobile app development. They can provide with a lot of AR features when you are building your native AR apps. But obviously, by default, they are accessible from the browser, and this is what WebXR aims to do. It connects the browser with those two libraries. And as a result, it gives you access to all the features that they provide. They do all the complicated stuff for you, like motion tracking, camera understanding, interactions, anchors, and other stuff that you want to track. Let's have a look how they work under the hood. I'm going to describe how these processes work in the ARCore, but I'm assuming that in the ARKit it's really similar, or probably almost identical. The most important part of world tracking the ARCore provides is simultaneous localization and mapping, also called SLAM for short. This algorithm builds a virtual map of the real world as the user moves the camera around. It slowly creates this world in its virtual space. So you probably know that when you turn on any AR app, oftentimes at the beginning it asks you to move the camera around. And this is the reason why. This algorithm needs to gather some data to see how the real world works so it could recreate it. The first step of recreating this world is choosing some feature points. That's usually like some points that stand out from the image, like some hard edges. You can see in the picture that you should probably choose like the edges of the sofa. And then when you move the camera around as instructed, the algorithm is also tracking the phone's inertial sensors. That means gyroscope or accelerometer. And that way it can calculate by how much you have moved when you are moving the phone. And all it needs to do is to compare by how many pixels did the feature point move on the screen, by what angle did you turn the camera around, and with some smart math, you can calculate how far from you are these points and how they are positioned relative in the world. Another important step is plane detection, or also called environmental understanding. Now that we have mapped all these feature points and we know where they lie in the surface, in the environment, we can have a look at them and see if some of them lie on the common surface. If they do, then it's probably they form some kind of plane. So here in the picture, the algorithm detected some points on the table, and it could see that in the 3D space they are on the same plane. So it assumes that there's probably some sort of surface that you can place stuff on. Side note, AR Core does only support horizontal and vertical surfaces at the moment, but there are some native libraries that build on top of AR Core, and they are able to detect diagonal surfaces if that's what you need for some reason. Building on top of that, we also have depth understanding. Some newer phones have time of flight sensors, which are the small sensors that shoot out infrared beams. They go into the room and then they reflect back. And based on how much time it took them to come back to the sensor, the phone can calculate how deep the scene is in that point. However, if we get like all the informations that we gather above from the previous steps, we can calculate the depth even without the sensor, although they help a lot. And once we get information about the depth, we can do cool effects like this, that it can block our virtual content with the real world content. Now, light estimation. This serves to analyze the lighting in the scene. Correct lighting is very important in augmented reality experience, as it can pretty much make or break the illusion or the 3D model belonged in the real world. The algorithm looks at the visual cues and tries to approximate all the different properties of the light, like ambient light, reflections, shading, etc. Here you can see a nice demo of light estimation in AR Core in action. Not sure if you can tell like right away, but the mannequin on the left is virtual. And you can see as the light moves around, it changes the shadows and the specular lighting and everything. So it's another very cool feature. Okay. So that was all very interesting. But how do you actually put it to, you were saying something, Razi?
No, sorry, I hit it by mistake.
Yeah, no problem. How do you actually put it to use in the browser? Surprisingly, it's rather easy. There are like few steps you need to take. First one that's not required, but you should probably do it, is you can ask if your browser supports the session that you need. In our case, it's immersive AR session, but you can also replace it with VR and you get the same result just in virtual reality. Although this one function in particular doesn't really work with current implementation, as it doesn't. Oops, I'm sorry. Can you hear me? Yeah. My headphones just turned off randomly. Yeah, so this function doesn't really differentiate between VR and AR at the moment. So if you are in a rare case where your phone does support VR virtual reality, but doesn't support augmented one, it will still return true, and then it will fail later. So if your phone does support AR, you can just request the session in a promise, and once the promise is fulfilled, you can set up rendering function as a callback and just render all of your virtual content within that function. Just a disclaimer, the code that I'm showing and the other code snippets are extremely simplified. I'm obviously moving all of the stuff that's not specific to Pxr is just boring and would distract from the actual important content. Anyways, the previous code was easy, yes, but who really wants to do any kind of rendering from scratch? Luckily, there are some libraries that already support WebXR, and in this presentation, we're gonna use Three.js. It's a library that's used to create and display animated 3D computer graphics in browser using WebGL. We use it in Salsita on several projects, so you may be already familiar with it. One cool thing that Three.js does for us is that it replaces all of the Pxr initialization with the simple button that's part of the Three.js library. You basically just create a button, you add it to your document, and it takes care of handling all of the initialization stuff like requesting the session and making sure it's compatible. And if the browser doesn't support, if the browser does support AR, then you'll get this nice button on the bottom of your website. If it doesn't support AR, it will just say that it's not supported. I'm going to go over several demos that are available on Three.js, and we will demonstrate on how you can build WebXR on those demos. Okay, we mentioned that augmented reality should be interactive, at least to some degree. So how do you actually handle the interaction? Once you get into the session, you can create this controller, or rather you can request a controller from the XR session. You can think as a controller as a virtualization of the virtual reality controller. So you may have seen in some VR headsets come with those VR controls that you hold in your hand, and you can click on the different stuff in the virtual reality with them. So if you are making a VR experience, you would use the same code, except in AR mode, this controller would be created on the spot whenever you touch the screen. This number basically means which touch it is. So if you get a controller with 0 index, the first touch that you do on the screen will create this virtual controller in the AR environment. And then you can simply add some listener to the controller and give it a callback. In this callback, we create a new mesh. A mesh is basically just a 3D object. In our case, the geometry of the 3D object is going to be a cylinder. And we set the position of this mesh, of this 3D object, to the position where the controller is in the world. And also we will set its rotation. So what it's going to do, well, in the end, we're going to place the mesh in the scene. So in the result, whenever you click on the screen, it will trigger the select event. So this callback will run through, and it will place cylinder at the point where you touch the screen. We can have a look on how it looks. Hopefully it will be visible through screen share. So you can see that I'm place tapping the screen, and whenever I tap the screen, it creates a cylinder. You can see that it's positioned on the place in the world where I tap the screen, but also it's rotated towards the camera, since we also set the rotation of the cylinder. So just with those few lines of code, you can make cool stuff like this and place objects in the virtual in the augmented reality. Now, we added the objects on the place where we tap the screen, but I did a whole spiel about world tracking and plane detection. So it's much cooler if we actually place the object on the ground, so it would make it feel like it's actually part of the world. For that, there's a feature in Pxr that's called hit test. It's basically raycasting, but for some reason it's called hit test in Pxr. It's an advanced feature. That means that you have to request it together with the session, otherwise it won't be available in your XR session. So if you want to find out where you are raycasting from the camera phone, you first need to create hit test source for which you need reference space. But basically, those two lines of code will create this source of your hit test, of your raycast, in reference to the virtual world. And then you can take this source and just use it in your render loop. So in our render loop, it's pretty simple again. We just make sure we have the frame so the render loop is running correctly. We checked if we have initialized our source, and then we get the results. It has results, array of results. So if there's any element in the array, we take the first one. In augmented reality, I don't think there's a case when you can get more than one result, because once you raycast from the point that you touch the screen, it will just go forward and it will hit one plane. If there's another plane behind that plane, it's highly unlikely that your AR library actually knows about the plane if it's hidden behind another plane. However, in virtual reality, it's possible to get more results, since the world can be more complex and not just a simple approximation that you have in AR. Right, we take the first result, that's a hit, and we can get the pose of the hit. Pose means it's a combination of its position and rotation. All right, I forgot to mention that in this example, we're going to have a reticle. A reticle is going to be a simple 3D object that will be placed in the world on the spot where the camera is, ray from camera is intersecting with the ground. So whenever we get any hit with a plane, we will display this reticle. And if we don't get a hit, we will hide it. And also, if we get a hit, we position the reticle to the position where the hit occurred and also rotate it accordingly. And then you can just use your standard render function. Okay, how it looks in the real life. You see, once I got some hit, some intersection with the ray from the camera with the ground, I get this reticle displayed on the ground where the intersection is. Then I can combine it with the first example and just use the detect whenever I tap the screen and place the object, but instead of placing it on the control position, I can just place it on the reticle position, and that's how I can position different objects in the world on the plane. Light estimation. Light estimation is surprisingly easy, considering how hard it is to actually estimate the lightning from the picture. Since it's mostly a nice to have feature, we don't need to specify it as a required feature, just as an optional one. So in a case that it's not supported by phone, the request for the session will still go through, and we will enter our session without failing. It's just that we won't have access to this feature. As part of initialization, we can create some default light with some basic settings to act as a placeholder until we get the information about the lightning. To get the lighting, it's the estimated light. It's really easy, like I mentioned. 33JS, there's an object tool, Pxr estimated light, and you can just initialize it, add a listener to it, and whenever it starts estimating the lighting in the scene, it will trigger estimation start event, to which again you can just subscribe, and at the start of the estimation, you can remove your default light, add the Pxr light, and you can also check if the Pxr light contains environment map. Environment map is a texture that's used for displaying reflections on the object. So in simple terms, when you have object in the scene that is reflecting something, you want it to reflect some image, but you don't necessarily want to, you don't necessarily need to have some other objects in the scene that would be reflected in the object. You can just have a texture that will be only seen in the reflection of that object, and that's something that can be estimated with the AR core as well and WebXR. Let's have a look at the demo. So in this demo, we have 9 cubes that have a metallic type of surface, so they are highly reflective. And you can already see that the light estimation algorithm is detecting that somewhere around this position should be a reflection of some strong light. It's probably like looking at the background, looking at the highlights of the objects of the background, and then try to simulate it with its estimated light. So I can turn on the lights, and you can see that suddenly it all got brighter, almost as if it's reacted to the actual light that I have in my room. And it really gives you a feel that those spheres are actually with you in that world. Last and least is this seemingly most simple feature, but it's also least supported and least documented, and it's the overlay. It does exactly what it sounds like it does. It lets you place some DOM layer over the AR session that you have in the browser, which is normally not possible, as when you enter AR session, like all the DOM that you have is removed. So this is another advanced feature, so you need to request it. When you request a session, this code is actually taken from Kila. We use the DOM overlay there, and also the demo is going to be from Kila, as it's not on 3JS. It's not in the 3JS demo website. Another thing you need to specify when requesting session with DOM overlay is DOM overlay element. You can just use React reference. So here we specify that we want to have DOM overlaid with root that's called AR overlaid element reference. And then later in our code, we can make a div element, give the same reference so it can match it and style it however you want. Generally, you want to hide it like this when you are not in the AR mode, so it only appears when you are actually viewing your world through augmented reality. The example is pretty simple. This is the app without AR mode. And when I press the AR button, I get taken here. And those two buttons are actually simple div elements. This one is actually a button element. So that lets you make a pretty simple interactable UI, which otherwise would not be possible, or would be rather much more complicated, because as you can see, if you would press on the screen in AR mode, it would only be detected as a control interaction. So you would need to make this kind of UI without DOM overlay, you would need to have actual 3D button in the 3D world, and that's just a lot of headache. So this is kind of cool, saves you lots of time on the UI. There was a brief rundown to Pxr features, and let's say that it's all pretty cool, but you want something simpler. Like you want to have a model viewer that you can let your customers display some kind of model, but you don't want to go through implementing all of this feature that I just mentioned. There is a simple solution for that. Luckily, both Google and Apple thought of it and came with their own native model viewing applications. They are called Scene Viewer and Quick Look for Google and Apple respectively, like Android and iOS. So if you just want to display a simple model that you don't want any complex interaction with, other than just moving, rotating, and possibly scaling, you can use that. And you can use it in both native apps and web apps. From web app, let's start with the Scene Viewer, which is the Android one. For web app, you can just insert this rather simple link into your web page. You can see that this link is a little bit complicated, but it's not really nothing too hard. And then when you click on it, the Chrome will realize that, oh, you want to display this model, and it will open the Scene Viewer app that's mostly pre-installed of most of the Android devices. And that way you get this app, which is native. The model that is supposed to be displayed is included in this URL. The app will download it to display it. And then you can move it around. It will stick to the ground. You can rotate it. You can resize it. Although you can disable the resizing in the initial setting. That can be useful if you have a like furniture in this case that needs to have some that is going to have some specific size, and you don't want the users to resize it however they want, so they won't get confused about its actual size in the world. Yeah, and here you can see example how to implement it in Java if you want to make a native app. Again, super simple, few lines of code. Quick Look is iOS alternative of Scene Viewer. It's even simpler when it comes to the web link. You basically just give it a rel property, specify that it's for AR, and link it to the model you want to use. You can use some preview if you want. And then if you just click it on your website on your iOS phone, you'll get taken to this application, which has pretty much the exact same feature as the scene viewer, that you can move, resize, rotate. You can also just cancel AR mode and go to the object mode and just see it on a regular virtual space. It can be useful if your phone doesn't support AR. But if you want best of both, or even three worlds, actually, there is this library from Google called Model Viewer, and its purpose is to display 3D models. It can also display them in augmented reality, and for that it tries to use Pxr. That means that's it, like primary, like the first thing it tries to do is to try to create its own Pxr model viewer, so it's right in your browser, so you don't have to be switched to the other application like with Scene Viewer or Quick Look. But if your phone doesn't support Pxr, then it will fall back to the Scene Viewer and it will open the model in the Scene Viewer or Quick Look, depend on the platform you're on. And it's also super simple to use. You just include it in your HTML, and then you can use it like this simple element. You can specify what kind of feature, what kinds of fallback you want to have there, and it will work straight out of the box, pretty much. Okay, I think I've covered most of the libraries that are relevant in the current environment of AR apps on the web. Here are some links if you want to see my sources, or if you want to read further about how the world tracking works, light estimation, or if you want to see the samples that I showed you before. And I think that's pretty much everything from me. And if you have any questions,